Right, looks like we've reached 10, and I do have some reports from Matthew, which I've put on the whiteboard. So zoom in and make it look good, however you need to, and then we'll have a copy of the whiteboard. Anything you guys want to add is totally okay. If you have images or anything like that, and I know that either Martin or David might have some slides to share. So there should be sharing should already be, yes, it's already turned on. So when we very shortly, very soon, we'll get around to that to talk about the AMSAT UK MDT project, then slides are totally welcome and they'll be shared with everybody. And welcome, Aaron. So welcome everybody. This is Open Research Institute's weekly projects meeting. And what we do is we go over what we've done over usually the past week or so, and what we are going to do, what we have planned to do over the next week or so. And then if we have any roadblocks, so we share like things that are in our way that are preventing us from getting things done. And then anything that ORI, specifically Open Research Institute, can provide. If there's either something you need to find out, or maybe potentially something that needs to be bought, something with molecules, that sort of thing. And so what we'll do, I'm going to turn the floor over to Aaron because I know that he has some time constraints here. And Aaron, you have the floor.
Thank you, Michelle. Um, I had some unexpected work trip happen last week, so I haven't had a lot of time to focus on the project. But what I do plan on doing is continuing where I left off, which was implementing the DVB-S2 encoder on a different FPGA, specifically the ZC0104 with an FM comms board on it. I got the hardware, I got the encoder on the hardware, and I can toggle its registers using OpenCPI. But what I've been kind of stuck with, not necessarily stuck with, but I'm in a point where I'm thinking of deciding to, because there's two, I guess, what I'm trying to do is get null packets to from the PS side into the PL side, such that it can be received using the BATC DVB-S2 decoder, and the blog post that I made the other time used video to prove that the link was working. But I'm at a point where I mean, ultimately, we want the GSE, DVB-S2 GSE, to encapsulate IP traffic. That I think you mentioned last time I was in the meeting that it was easier to implement that than it is the TS, the transport stream version of it. So I'm coming to that conclusion as well. So I think I might move over to that. But the kind of wrinkle that I was in was that the Pico tuner that I built was not able to get GSC to get through, but I did get all the parts to do the mini tuner, which was the previous iteration of the decoder. So I have the parts, so I have to build that and then validate the GSC implementation from Evereast, and get that path kind of sorted out in a happy path and a known working path, and then go back to implementing the GSC portion on the PS side to get that all up and running. So there's a lot to do. I'm not necessarily sure that, I mean, ultimately it'd be nice to have both to be able to do video and data, but our ultimate goal is just to do data. So maybe I should just focus on that to get that implemented. I guess there's not necessarily any resources I need from ORI, but yep, that's where I'm at.
Wow, that's a lot. Yeah, and near and dear to our hearts. Let's see, anything that you can think of, Paul, particularly with respect to GSE, is there anything that we might be able to say today about the effort moving forward?
I'm sure there is, but I don't know enough about exactly where we are to say what would be next. And we have not looked
But
at it in a
I
while.
guess maybe some confirmation, like, I mean, that's makes sense
Yeah.
that we should focus on the GSE, or is the
Yes.
ultimate goal to be able to implement both, or
Both
um,
GSE and MPEG, you mean?
yeah, the MPEG transport stream.
Yeah, MPEG so tuned for broadcast and all it has all sorts of amazing things in it for the sort of communications that we're wanting to do. GSE is the right answer, and you are definitely on the right track. And you know we've we've moved things forward in a couple of different ways over time, and it's always worked out better for us. There's nothing inherently wrong or bad about MPEG. It's just for a different use case. And GSE is the right answer for what we want to do. And it will unlock a lot of amazing things. Unfortunately, the path requires a machete and some and a good strong back a lot of the time. But this is an area that we care very deeply about, and we can pitch in and help wherever there isn't anything that's been done that we should be paying attention to. So yeah, for sure. I think you're on the right path. Um,
Yeah, I would
Okay.
agree that as long as what you're interested in is the different kinds of data, then data over GSE is definitely the winner over data over MPEG. The only exception to that I can think of is some kind of backwards compatibility situation, because there are still some devices out there that know how to do data over MPEG that don't know how to do data over GSE, but you'll find them to be pretty scarce nowadays. So you might as well go to data over GSE.
Okay.
Yeah, and for those
Thanks.
following along that are interested in this sort of thing, the GSE expands to generic stream encapsulation. This is a drop-in replacement from the DVB folks, digital video broadcasting suite of standards. There's a lot of them. They're all open, and most of them are really good. And so GSE is a drop-in for MPEG, which is widely used for video broadcast, usually one-way commercial broadcast. And so GSE reduces the overhead. So it's a win in terms of reducing the overhead, and it's also a win in terms of flexibility. But it's a sort of you must be you're gonna have to bring a little more of your chops to the table to go ahead and do the implementation. There's fewer I would say fewer implementations of this. It's all kind of laid out for you and makes a lot of sense. The GSE standards, well done, meets the needs. But the things that Aaron is spearheading here and getting done not just for open source digital radio work like that we do here, but also from an open CPI perspective is going to seriously pay off. But yeah, this is it will be some stiff going to kind of figure out the values in the implementation, and that's exactly what you're doing. So yes, you're on the right track. And if there's anything that we have not done yet, or that you go, hey, if you could uh, step up and do this particular bit of VHDL, that'd be great. Then please just let us know because it'd be good to be
Okay.
able to prioritize that type of work and then meet you, um, you know, like where you are.
Yep. Yep. Sounds good. Thank you.
You bet. No, happy to help. This is really super exciting. Oh, and why don't you tell people a little bit about OpenCPI, what it is, and where to go if they want to find out more about it?
Yeah, so OpenCPI is a component-based framework for not only for doing projects and its primarily focus is software-defined radios, but it's not necessarily need it be a software-defined radio. But the idea behind it is you build your application once and you're able to deploy it across various different types of platforms, varying different types of FPGAs as well. So in our example here with Opulent Voice and with the WS2 encoding, that we can move that great IP that's been created onto different platforms, and not just the Pluto SDR, but bigger platforms or maybe other variants of the Pluto SDR. Make that process easier. To find out more information about it, you can visit our website at opencpi.org. And that points you to it's a completely open source framework, and we try to abstract the FPGA and general process units in such a way that it's portable. You can move your components across the different processing elements in a nice way. So, yep, check us out, and trying to get a usable example with the stuff we're working on here, so people can get hands on it, and understand a little bit better. Thanks, Michelle.
Oh, you bet. No, happy to help. And thank you so much. This is exciting stuff, and looking forward to it. The sort of work that you're talking about doing. So I've made a couple. Ever so often, I go out and make like a little foray, because we do use the Pluto SDR for the target for Opulent Voice, and it's a good development platform. But ever so often, I go out and do a Linux build for the ZCU 706, and anything that could make that easier is would be wonderful, because it is actually a lot of neurosurgery to get that to work right. And I'm very much looking forward to being able to deploy and test things like Opulent Voice and the high-fidelity on all sorts of different platforms, maybe without the hours and hours of
Yeah,
undocumented TECL script manipulation, etc. So that's a huge win from my point of view. And yeah, no, let us know if there's anything that you need to make
yeah,
any progress.
yeah. So
Yeah,
specifically in that regards, as far as the way the framework kind of views like the Linux builds, is that we build it once for the platform, and we rarely even touch it. And a lot of the applications that we build get cross-compiled from a development host for that specific architecture, whether it be the 32-bit version or the 64-bit version of Xilinx Linux. We use the cross-compiling tools, and then we move all the artifacts over there to run on the platform. But yeah, the way that we handle that is a little bit different. We don't have to build it every time, essentially. So it might help in that regard. But
definitely. Even on a
yeah,
fast computer, these builds take kind of a while. So
yeah.
yeah, it's a big win. Thank you so much.
Hmm.
All right,
You're
anything
welcome.
else, Aaron, or any other comments or
Nope.
questions?
I'm good. Thank you,
Okay.
Michelle.
Yeah, thanks so
I
much.
guess one last thing. My meeting that was at 12:30 no longer exists. So I appreciate you putting me on the beginning of the lineup, but that's no longer not necessarily a requirement, but no longer needed. Thank you.
Oh, yeah, you're very welcome, and a good deal.
Yep.
Awesome. All right, I have a quick update for Encozy. So Encozy has worked on the shortened HF antenna, which is a really super cool project. So I just want to let you know that the article that you reviewed was submitted to QEX magazine. This is ARL's Experimenters magazine. So I went ahead and submitted it. I've gotten an acknowledgement, but no schedule on when they might publish it. But that's going to move forward. Failing that, there's a couple of other places where the work can be published, and yeah, just looking forward to seeing where that goes. I was able to give a presentation about the shortened HF antenna to amateur radio group, and the response was pretty strong, positive. So hopefully we'll continue to get this moved forward. So I know that's one of the things that you have been involved with and interested in. So I just wanted to let you know that it actually did get over the wall, so to speak, and is in review.
All right. Good to hear that it's making some progress. Fingers crossed that it actually successfully goes through.
Yeah, it might. It's right up their alley. And yeah, for those just hearing about this now, so we do a lot of microwave FPGA work, but we also look at antenna designs, and we've done like 3D printed microwave surfaces and metallizing 3D printed materials. It's actually pretty straightforward, surprisingly, and so we do that sort of work a lot. But we also took a crack at a shortened HF antenna. The original idea is it's sort of a it's linear folding. It's not a linear load. So this is not a coil. This is actually
Mhm.
linear load. And this original article was from 1958 and was from the UK amateur radio group. So this is from the National Society RSGB. The 1958 article is fantastic and really kind of laid out the whole idea. Uh, a couple of folks have taken a crack at this over time in the late 1980s, early 1990s. There's a fellow who used this exact technique to make a HF antenna he could take on the road on travel that fit into a three ring binder. So this was with copper tape and, leads, and you just set it up in a hotel room and made contacts successfully all over the world. So we're hoping that this article goes forward. It kind of ties in all of the amazing historical work done in HF antennas in this particular aspect. We did some MATLAB modeling and kind of ran it through the ringer, but we went ahead and built it and then tested it over the air. And Encozy also has done this with Shamudra and on the East Coast. So there's two prototypes here that's in the repository, recorded and presented there too. So oh yeah, we're moving it forward, and we're looking, and I know you all are looking as well for someone that can help scale up this HF antenna design, because everybody's really interested in compact HF antennas, especially for 160 meters. That's kind of the missing link in HF antennas. If you want to be on this band, you are faced with a really enormous antenna. And if you are in a city or suburban lot, this is not really an option to do a full size antenna. So this actually may work. That's kind of the next area of work, is to kind of look at that. So if you're interested in HF antennas, that's something that we do. And there's a whole team of people, Nkosi and Shamudra and me and some other folks are interested in moving it forward. So the invitation is open to chip in and specifically look at 160 meters. So that's to include that in the original design. 160 was a little bit of a reach even with a tuner. So we'd like to look at what it would take to make that easily happen. So thank you, Nkosi, and just wanted to give you the update. Anything else from your end that you wanted to talk about?
Well, yes and no. Yes, in that I've been combing through a few of the projects, honestly, just to see like what piques my interest. Besides the high Ferrari thing I got from Shamudra, I read through the documentation. He explained some of it to me. I went through the GitHub and saw the PowerPoint presentation as well as a few updates that's been done. Just I've been going back and forth between that and asking him and going through how exactly it would be implemented and how it could be improved upon. So there's that. But also another thing that piqued my interest is your, what is it, opulent voice? How is that going to be used? In particular, could it be used for like, well, thinking in the future here for some like Earth, Moon, Earth link, or is it just strictly for like terrestrial use? How applications wise, like what would it be used for?
Okay, so this is a high fidelity digital voice link.
Hmm.
So the traditional sort of ham digital voice is uses very low bit rate codecs, and for a while, that's this has been our main critique. So our main motivation for doing a lot of this open source digital work has been the very poor voice quality of low bit rate codecs in amateur radio digital voice. And it's not just amateur radio digital voice that dates all the way back to the original P25, which used this P25. So Project 25 was the main protocol used for public service, emergency service workers in the US. It's decades old. And low bit rate proprietary codec, AMBI codec. We have AMBI 1.5, AMBI 2.0, AMBI 2.2. So there's a whole family of codecs that have increasingly added bit rate and added innovations in terms of the voice coder, but they're proprietary. There's at least one open source alternative low bit rate, and that's Codec 2, and that's a direct sort of competitor for AMBI, but it tops out at about they're at a low bit rate. We're talking, 3,200 bits per second, 3,400 bits per second for the sort of the AMBI codec 2. There's another open source codec, voice codec, and that's Opus, and it goes all the way up to music quality. This is the choice that we went with, and what we did is we said, okay, we're going to give a modest improvement that gives you really nice voice quality. The complaints from public service workers like firefighters, police, are that they can barely recognize people on the radio. They have to frequently ask for retransmissions. This is the codec that we're using for amateur radio digital voice. That's not acceptable, especially not when you move away from 2 meters. Above 2 meters, you do not have to put up with this limitation. You can use a higher bit rate codec. On 70 centimeters, we can use the 16 kilobit per second codec, Opus codec that we're using in Opulent Voice. So in terms of the motivation for the protocol, that was one of the initial strong motivations. That is the fundamental reason why we've done all this. You do have to give up 2 meters right now. That may not be the case if the rules changes go forth and the bit rates and baud rates and stuff like the bandwidth limitations change for 2 meters. But we viewed 70 centimeters and above having really nice voice quality, almost music quality at 16 kilobits per second. A little bit herky jerky, but the voice quality is a significant improvement. At 32 kilobits per second, it's even better. That's kind of one of the paths that we are looking at maybe in the future, but 16 kilobits per second is what you get. There's no excuse at microwave for using a 3000 bit per second codec. So that's the reason. To answer your question directly, Opulent Voice can be used point to point terrestrially. It can be used in a repeater terrestrially. It can be used with space communications as an uplink. That's what we use it for in our satellite system. So that's our native digital uplink. And it is a minimum shift keying modulation, which is a constant envelope and amazingly wonderful, you know, just by that. Also, no phase discontinuities at all. So minimum shift keying, you get these benefits. It is more complicated. It's a little more difficult to explain to people and to construct and deconstruct with a modulator and a demodulator. The main lobe is a little bit wider than QPSK, but all the side lobes are much lower. So your filtering requirements are relaxed. So we were talking for a 54.2 kilobit, bit rate. That's what you get for, with all of the layers and all of the protocols and all the stuff that we put in order to make it really useful at the application layer. You end up with about 81 kilohertz null to null. Okay, so it sounds like a lot, and it's a little bit more than if you had an equivalent just straight up QPSK signal. But the
Mm.
benefits are pretty significant. So that's why we have went with it. And so it's terrestrial in space. It can be used point to point, which is what we're demonstrating today, like in the lab. There's a repeater system. So we have a repeater simulator that's up and running on the Linode at ORI. And that gives you an idea about how it would feel to look to use on a spacecraft. The protocol itself, so apart from the things that I'm talking about with respect to the voice quality and all that, but the protocol uses voice and will interleave voice keyboard data and control messages without having to switch to another mode. So there's no clunky second packet mode. It just knows what is being sent, and it uses priority queues. Voice always gets highest priority, so you always hear live voice. And the applications that we've written to receive it will take the voice and it will allow you to replay it. So there's a little UI bubble in the HTML, so all HTML interface. So you don't need to install a program necessarily. You can use a HTML interface to your radio. You get a replay bubble, so you can replay the audio, and it also does a transcription locally using open source tools. So that's kind of like the use case and sort of the motivation where it can be used. The uplink, when it goes up to the satellite, so we consume this protocol, and then we do some decisions about like, okay, we're going to pack a downlink frame, and that's the DVB S2 frame that Aaron addressed. That's what he's directly working with, is this downlink. So it's a frequency division multiple access uplink with all sorts of people talking in different channels. Paul has written some really good code and some descriptions here on how that's managed. And then it's packed into frames and then sent over the downlink. So everybody can hear everybody on the downlink. And that's the high-fidelity, that's our satellite proposal. But Opulent Voice can be decoupled from that. You don't just see it in the uplink to our satellite part. You can also use it as a terrestrial repeater or a point-to-point. So does that
Yeah,
all
because
make
I was
sense?
thinking, oh yeah, because when I was reading both of them simultaneously, I was wondering, are these separate, or it sounded like they could be intertwined and used together. So I was wondering how like any system integration is involved in these two.
Yeah. No, good question. Thank you. It's nice to be able to kind of go through the basics and to get it explained. So yeah, very much appreciate the question. But
All
yeah,
right.
if you want to chip in to Opulent Voice, there's a channel on our Slack about it, and lots going on. The images here in the whiteboard, this top one that's the network graph is the current sort of tip of the spear of the Pluto MSK. So we're targeting the Pluto SDR for the first sort of like implementation to get it working over the air, because that's the only way that you really find out a lot of problems. And the good news here on this graph is that we're now down to one branch instead of like seven, and the recent steps forward have been significant. So here's kind of the proof of life for the activity about the branch management, checking, check them out, work on it, write a pull request, that sort of thing. So the history is pretty good. We try to write good pull requests. Here, a little bit lower is a summary of the most recent problem that has been solved, and that was missing T-lasts. We use AXI bus to communicate to ship frames back and forth, up and down the receiver and the transmitter. And we had a very interesting bug about the T-last, which is a marker in the AXI protocol. This says, okay, this is the last byte of your frame. That's very important to know. If you have a frame-based system, like we do, every 40 milliseconds a frame comes out. You really need to know inside your transceiver and inside your basically at any level. You need to know when the last byte was, so that you know when the frame ends, so that you can start doing things like, oh, I don't know, reversing the forward error correction, or presenting it to the next part of the process, or unscrambling it, or whatever you have to do. And the TLAS was in the wrong place. And this was blamed for messing everything up, for preventing an over-the-air demo to go forward. Well, it turned out to be part of the problem. Yes, missing TLAST, or the TLAST being moved to the front of the next packet, was when, and it took a lot to fix it. It was a kind of an insidious and difficult bug. Didn't fix the problem. The problem turned out to be that the DMA controller was misconfigured in a Teckle script that really belongs more to the HDL reference design from analog devices. So this was a very twisty tale. It took weeks to figure all of this stuff out. And I just have to say that if Aaron's OpenCPI can prevent this sort of stuff in the future, then it will be a huge win for everybody doing any of this sort of work. So that's sort of our report. Just over the past week, a lot of this stuff has happened. Over the past week, also Matthew could not be here, so he's another one of the FPGA authors. He's I would say probably the owner of the modem of Locutus. And he says he's working on a status register request. We requested an additional status register, which has to do with frame synchronization. So when you talk about bits and synchronizing to the bit level in a digital signal processing sort of thing, you have to find out where the edges of the bits are, and you're getting the bits into your stream. Well, what we've added is frame, at the frame level, and we have a sync word that indicates, hey, this is the start of the frame. And adding all of that adds some complexity. We have what we call a flywheel approach. So there's some hysteresis there, where it takes a little bit to convince the system it's locked. Then it relaxes the requirements. And then it takes a little bit to convince it that it's lost sync. So this sort of behavior has some registers. There's like 4 registers in there that monitor this sort of stuff. And we needed visibility into it because nothing's working. It worked great in sim, falls down flat on its face on hardware. So we requested a register, added this to our register map in order to show what's the internal behavior. And yes, so we did solve the problem. It turned out to be that weird DMA controller. It was paying. The details of that are, we told it to pay attention to an external synchronization signal that does not exist. So it would simply never forward the frames to the processor side. So Paul had nothing to do on his processor side code, and nothing ever came out. Even though it looked perfect in sim and all of the frames are going somewhere, the hardware is not timing out in the way that we expected. So it was really fun. Anyway, this register is coming, and there was some issues with getting the register in there. So there's probably a whole other story there. He's also looking at implementing clock domain crossing on the AXI bus. So the bus for all of the registers. We do a lot of clock domain crossing when it comes to the data. So when we're shipping the frames over, there's a what's called a dual clock FIFO in our design, and we're very confident that this is working great. This is a fully open source version that's also done by Xilinx IP, Cadence IP. All the companies have a block that you can just use for this sort of thing. Ours is fully open source, so clean and clear code. Um, but when we talk about the registers, there's also a clock domain crossing for the registers, the control and status registers. And that's different than the way that we do the dual clock FIFO for the data. So now we're talking about doing that sort of approach for the registers as well, because external registers cause the Pluto to brick. I say brick, crash. And Paul then dug into this and wrote a really nice article, which will come out in probably November or December newsletter about how to reverse your Pluto being completely bricked when you do something like this to it. So lots of, if you can think of this as like a plant with like roots that go into different pots, because you've got the actual code affected or HDL for the project, but also like the modern way of getting your Pluto unbricked, is different than the way you used to do it. So his article is actually a pretty good update for that sort of process. And then finally, he's looking at a Costas loop lock algorithm that also provides an estimate of the energy of the symbol divided by the noise power. So if you've heard of EBNO, that's the energy for bit divided by the noise power. This is SNO, so the symbol divided by the noise power. So it's really cool. What we're doing is we're adding indications that the Costas loop in the demodulator is sure that it's got a bit by the tail. So that's what Matthew is up to. It's unfortunately a conflicting meeting and couldn't be here to share it himself. But thank you so much, Matthew, for all the hard work. This is not easy stuff, and Matthew is he's already talking about an article for the newsletter to kind of share all this and explain it to make it a little more accessible for folks. And I think that's all I've got. Is anybody got any questions for me about anything that I've said? Anything that I might have gone over too quickly, or that was too confusing, or that I missed? And if not, then I will turn the floor over to Paul to bring us up to date on the stuff that he's doing in any sort of remote lab. And then right after that, we'll turn the floor over to Martin.
You know, um, I can't say enough about how Michelle's hard work has led to this success that we've achieved. Um, she has been completely diligent and relentless at hammering on these FPGA problems. And finally, we have a configuration that works as far as we can tell. And we haven't looked too carefully at it yet. Personally speaking for myself, I've been sort of basking in the glow of something that worked. And then when we focus attention back on it, we'll probably find some more problems. But for the moment, it works. So yay. By work, I mean that my receiver, which is receiving frames, actually does receive the frames. The whole system, end to end, seems to be working using the test software that is aimed at debugging. And the next step forward on that is to switch over to the test software that's aimed at functioning like the real software. So the way we've been working together is that Michelle has been in charge of the HDL and the tickle scripts and all the build requirements. And I've been writing, we're modifying and slowly evolving C software that operates the system from inside the ARM processor on the Zinc. And this is the simpler part, fortunately for me. Uh, but often there are things that need to be tried when we have a puzzle, and there are lots of puzzles in these because it's almost a black box kit every time you build a version, and we need some way to uh, visualize what's happening externally. So there are all kinds of weird side paths and dead ends and experiments to run. Um, so as a consequence of this, the workflow has been that Michelle would create a build, sometimes with great struggle, but a build would come out, and then I would wrangle the Plutos and try to get the right thing loaded into both Plutos and maybe modify the software to reveal whether whatever the latest thing was that worked. And hopefully that would work and we'd learn something and move on. And that with iterating in that fashion, we made it finally to the point where things seem to be working. And as a side effect of that, I've got a nice collection of Pluto builds in the form of pluto.frm files. Um, and I've tried to give them suggestive names as we went along, but we didn't always know what we were doing as we went along. So some of the names are kind of bad. Some of the names have the commit code that we use as the identifier for each build built in. Some of them don't because I didn't know for sure what it was when I named the file.
Like really final build, final.
Well, it wasn't quite that bad, but we, to the extent that we remember the history, some of the names are suggestive. So, so this sent me off on a tangent to write a utility because I really wanted to know what was in all these Pluto.frm files, and they don't do a good job of self-identifying. They're basically black boxes. They're binary blobs. Um, but all the things that create them are open to me through open source, either from analog devices or from our own work. And so I hammered on it for a while myself, and I created a script. It turns out I could do it with just calls to Unix utilities, and it unpacks the pluto.firm file and uncompresses the bits of it and looks all through it and scrabbles through the file system that it would create when it was loaded onto a Pluto. And Michelle has just posted to the whiteboard the URL for the utility I wrote that actually puts out that hex, that little hash code that indicates what version of the build it is. So I'm happy about that and distracted me for a while. Um, there's more that could be done with that kind of a utility. There's one particular thing I'd like to dig out of the kernel image itself. Uncompressing the kernel image is not trivial. It's not always the same compression. Um, it's got decades of cruft on it. Let's put it that way. So if I can figure out how to uncompress all that stuff, then I'll have a little bit more information, including who built the build and where. I mean, I know all of these were built by Michelle on the VM we call My Melody, so not necessary for the moment, but it'd be nice to be able to extract that information too. So that's what I've been up to for the last few days uh, since we crossed the boundary of working. And I'm also taking some of the changes that have been made in the process of debugging out of the C file that uh, is debug oriented and picking the ones that I think I need and moving them over into the other C file that runs all frame style that will be the model for operational software going forward. Yeah, because I want to do my next set of tests using that software instead of the debug software. So that's where it's at. Remote lab working as normal. Most of this stuff has been done uh, physically in the remote lab, but logically outside the remote lab, just because it's a little more convenient for me. Um, but remote lab is working, and we're using the spectrum analyzer and stuff and getting uh, good monitoring capabilities out of all that test equipment. I think that's all I have.
Yeah, thank you. That's a lot. Very appreciated. Yeah, we'll the let's see the link there to the Pluto-FRM-info is really neat. Solid readme. And then Dialogus itself, that's the ARM code program that we're writing for the processor side for the modem for the radio is also in at github.com Open Research Institute /Dialogus. So if you want to look at the C code that goes into the ARM, that's where it's at. So that's rapidly moving forward. I don't know if you've got the stuff that you've worked on over the past week checked in or not, but if you, the most recent name of the file is opulentvoice.c, and that's got the vast majority of the work is captured there,
Yeah,
moving towards a frame version.
the version I've been describing is the debug version is in opulentvoice.c. That I recently checked in dialogus.c, which will be the frame-based version going forward. And it's still considered a work in progress, which is to say it hasn't been tested yet. Um, so don't take that too seriously as the truth, but that's where we're at right now.
Yeah. And soon the goal will be end-to-end over-the-air testing. We'll probably, I'd like to start trying to separate the radios and put them in different physical locations so that we totally have, a, prove a radio link. I think that would be fun to do, but also probably reveal a lot. And then we've started talking about filters. So the filtering that's done in analog devices, radio chips there's pretty stiff digital filter potential in there that we'll take advantage of. But when we start talking about actually transmitting over the air, the practical filter requirements are going to come right up, and we'll start publishing work about that too. So that's in the very near future. Yeah, thank you. Okay, and we're very lucky to have Martin Ling here today, and he is from AMSAT UK, United Kingdom, amateur satellite AMSAT organization. This is the premier organization for amateur satellite in the United Kingdom, and they have a super successful history with the FunCube satellite and the FunCube dongle. So if you have been doing this sort of amateur radio, digital, open source work, you are probably familiar with the FunCube. And Martin's going to talk about a collaboration that we're doing with AMSAT UK, and this is the Mode Dynamic Transponder, MDT. So Martin, you have the floor. You can talk about whatever you like, explain anything that you think we need to know about, and go over stuff. And then I can also add that we've done some work from at least our understanding, if necessary. But the floor is yours, and we're very interested in everything that you have to say.
Okay, thank you. I should point out first, I don't really speak for AMSAT UK here. I'm a member, and I've been sort of joining in with the cause of the FunCube team for a couple of years, but I was not part of the team that built and launched those successful satellites. I've come in well after that, really I was just looking to see if there was something I could develop or contribute to a future mission. And the idea that I had was, can we do a transponder that is an SDR? So rather than just a linear transponder, something that is doing some decoding and generating a new signal and sending it back down, whatever that combination is. And we got into some discussions about how that sort of thing might be integrated into the existing FunCube design in a way that was sort of minimally invasive. So something that would tap off at the sort of splitter after the existing IF stages in the uplink path, and then feed its signal in the combiner going into the PA. So it's kind of independent payload that could just be turned on and made to do a thing. And most of the rest of the discussion about that is about what could we do with such a thing, and what would be nice to do with such a thing, and how much of it can we actually do in practice within the constraints of a 2U CubeSat design. At last year's AMSAT UK colloquium, which is part of the RSGB convention, I gave a talk about this project and some ideas around it. If you'd like to watch that, you can go on the AMSAT UK YouTube channel, and in the 2024 colloquium, you'll find a talk from me called SDR Transponder Update that explains the sort of ideas behind this. And I'm coming here from a very sort of inexperienced kind of place, right? I'm not an expert, here, but I'm set out the ideas behind this and the sorts of things we might want to be able to do, and sort of what I've got in terms of an approach towards that. And there's sort of three capabilities that I would really like to see this be able to do. The most important one is that it should be possible to update the software running on this thing on orbit, right? Because if you can do that, then once it's launched, we can spend years experimenting with what we can do with it. Whereas if we can't do that, then we're limited to what's on it when it goes up, right? So that is the key requirement. First of all, is we should have some way we can send a new program up to this. It's going to have to be in bits sent by different people over different passes, because we're just not going to have the bandwidth and the time to get it all up at once. That's fine. So it's got to be able to have some working kind of uplink and store mode and the necessary signing and integrity and so on to go with that. The most basic sort of capabilities that we would want is sort of simple store forward kind of operation that people send things up to it, and those are gathered, summarized, sent back down, whether in the same mode or some other mode, and so forth, so that people can make contacts through the satellite. And obviously all of that has been done before, but I would like to see this be able to do something that's new, right? And so the key thing I would like to see it be able to do is to deal with more than one uplink signal at once. A sort of relevant point here is if you ever played with the Green Cube satellite when it was operational, IO-117, people had a lot of trouble working that because everyone was trying to get into it at once, and it could only deal with one uplink signal at a time, right? So where I feel that an SDR transponder could really shine is to be sitting watching over a little chunk of bandwidth and decoding, it may be a very simple mode, but more than one of them at once, right? And then you eliminate that problem of everyone's queuing to get into the satellite during a pass. So that's the most basic sort of things we'd want from this. But this is sort of sitting in the context of some much more ambitious and conceptual ideas about what would be nice to have if we had enough capability, if we had enough compute power and so on a satellite. Obviously, not all of that is going to be able to do in a 2U CubeSat. The email exchange we had yesterday, I realize you're getting into the limits of that, and I understand that. But it's what can we do? And so there's been then this question of, okay, this is all nice to talk about, but what can we actually do to get started? And so the next thing I did after that talk was to work on a design for a development board. If I share my screen, I can show you that design. Is that possible?
Yes, you should be able to share. Let me know if you can't. It's turned on, but unclear.
It says I can't because you're showing a whiteboard. So I could
Okay,
also
yeah.
maybe
Let
post an
me.
image
I'll
to
shut
the
off the
whiteboard.
whiteboard.
Sure.
I can close it without it going bloop. Let's try it. There we go. All right, you should be able to share.
Okay. So can you see this?
Yes. I see a
Right.
rendering of
So
a PCB.
yes. Okay. So this is the dev board design as it stands. And so the concept here is that this is a way to prototype the ideas involved. I'll give you some context of where this would fit in the overall sort of architecture of the satellite. So I've got here my slides from that previous talk, and if I just jump to this one here, this is about, so I've got the block diagram there of the RF board on Funky 1, AO73, and you can see the sort of red and blue lines just sort of connecting this sort of theoretical idea on the right of what we're trying to build, a sort of hybrid transponder that's got both a sort of bent pipe linear transponder and an SDR subsystem within the same system. And so we would be tapping off at a 10.7 megahertz IF, down converting that to baseband, going into ADC, and then doing whatever processing. And the DAC would be feeding an up converter to go up to the, in this case, actually to the RF frequency to be combined into the power with a power combiner going up to the PA stage for the downlink. So coming back to the design, on the top left is where the IF 10.7 megahertz IF would come in. You have a quadrature sample detector, and then some baseband filtering and amplification into an ADC. And for the uplink side, we've got a VFO for the 2 meter band, feeding an IQ modulator that's fed by a DAC. And this dev board has been designed to have a very high-end baseband system. So 24-bit ADCs, fully differential paths, over 100 dBs of dynamic range, which is not something we're going to have the ability to make full use of with the kind of compute resources that we can put on the in the power budget of a 2U CubeSat. But you can also take this and just use it as a baseband, and pull out all of that data over USB through the microcontroller to crunch it on a big powerful PC or whatever, to see what's possible if we did have the resources, right? Because the sorts of things I'm interested in here are, to what extent can we pull out weak signal modes at low powers when there's strong interferers, relatively close within the sort of passband of this system. And in the talk, I showed some data captured from the Serpent satellite, sort of illustrating just how strong the interference is in the 70 centimeter band especially over Europe and over the east coast of the US and so forth. So that's kind of the motivating idea. So none of this is really intended as flight experimenting with what's possible and how to implement it. The microcontroller and FPGA on here is an STM32H7, and the FPGA an ICE40, and that's really just because very limited power budget, right? So the question is, how much could we do with that? Could we do some simple multi-channel decoding of a simple mode, without too much presence of strong interferers, maybe. Obviously there'll be some significant limitations in how we, can do the search for signals and so forth. But we could be doing things like sweeping a sweeping a search, slowly across the passband, looking for something rather than trying to receive every possible thing at once, and then allocating receive resources, that kind of thing. That's the kind of idea. In terms of power budget, there isn't really a hard number here, because this is something that could be sort of turned on, turned off, used in different ways, and it kind of depends what else is being done with the satellite, with the other payloads and so on. But provisionally, the estimate I was given for how much extra power we were going to get from the extra U, going from 1U to 2U, from FunCube 1 to FunCube Plus, as it's being called, would be about a watt. And so I wanted to see, what could we do within maybe half of that. So the idea is to do something within half a watt and see how much we could do. But this board design is also intended to sort of experiment towards what could we do if we had a bit more, and what are the sort of limits of the processing, the SNR, what comes out of the RFIF stage and so forth. So this board design is not complete. There's a few things that weren't finished, and largely because there was a lot of uncertainty about, what do we actually want to put on here? What is useful enough to start trying to develop something for? Because there's really a chicken egg problem here, between what hardware do we use, and then a lot of firmware, gateware development that has to be done to do that. And the weak point of this whole project as a concept is that I've not really had much handle on how to start that and what the right architecture looks like to even try. So when I heard from David, G0MRF, that you folks were interested in looking at that side of things, that's very interesting to me, because you've obviously got the know-how to do that sort of thing, albeit you're doing it at sort of, I think, different scales of compute resource. So my interest here is if there's a way we can collaborate, in which you're able to lead some of that work, and I can maybe contribute on the hardware design side, to produce dev boards and moving towards eventually prototypes and flight hardware. So that's kind of where I'm at with it, and I'd be very interested to hear more of your thoughts about how ORI can contribute, and if there's a good way forward here.
Okay, thank you so much. That was fantastic, and really super helpful. And yeah, I think I posted the, if I didn't, I meant to, the repository where your board layout, your board design is. So it's been published, and it's in KiCad, so people can look at it and track it and follow it. So it's a huge contribution to kind of moving these things forward. And yeah, I think probably the one of the most important things, that kind of most important requirement, or the most important constraint that we're dealing with, is power. So just like in mobile telephony, when you only have a relatively small battery in your device, everything is related to power consumption. And with a spacecraft, that is even more critical, because you are very, very far away from a charging port when you are in space, and you have solar panels, and that's pretty much it. So when we're talking about half a watt here, I think that's the number that you were working with. And that dramatically reduces the number of FPGAs that can really be put into the spacecraft. And the choice of the ICE-40 is a solid one. That is the go-to one for anything in this sort of around about half a watt, and that will meet the power consumption requirements. Maybe it hovers around half a watt with the combination that you're talking about. And this is about 5,000 or so lookup tables, I think, in the ICE 40. And that's enough to work with. That will get you quite a bit of traction on like the sorts of communications that I think would be exciting for operators. What it what it won't do is maybe some of the like the when we talked last night. So we had a really good email exchange about this, and the sorts of like observation or digging weak signals out of a bandwidth. Um, that's a that's a lot to ask of a relatively small part. What it probably can do, and I'm going to guess, is that there could be two or three simultaneous signals that it could then do in the time allowed. So what you do is you read in a bunch of samples, RF samples, and what you would probably do, since it won't do parallel, it doesn't have enough little neurons in there, or it doesn't have enough loops to do that. But what you absolutely could do, I believe, with the amount of memory that we could put on board, would be to have a circular buffer and then to go through, pick out the strongest signals, deal with that, pick out the next strongest and next until you run out of time. It could probably do two or three. And you know what? That's pretty darn good. That's way better than one, which is
Yeah.
kind of what you were trying to move past.
Yeah.
And
That's the idea.
anything larger than one is a win and shows that the design is sound. And doing it in ICE 40 is a good challenge. So I think that we can help with pretty much any of these sorts of things. The initially when this project was kind of pitched, it sounded like it was here's a matrix of different modes, and we want to be able to connect whoever to whoever. We want to be able to do a fast uplink and slow downlink, meter it out, and that it was exclusively kind of store and forward type of situation. So that's kind of that's what I walked away with from the AMSAT DL symposium, that was kind of but this sounds much more ambitious. This is much more signal theory stuff. I think, you're in your three or four things that you wanted. Definitely the being able to reprogram the device in orbit is that's just for an experimenter, for amateur radio satellite people. That's what we really want. We really want to be able to update the code in orbit, which is a whole other challenge. In orbit updates are difficult, and you're right, it would take a while, to kind of
Yeah.
get things done. Now that's been done before, but it's hard. But we're up for that challenge. I am confident we could do it. And then that opens it up. It makes it an experimental platform, much more than a kind of a freeze dried, here you go, here's your system fusion repeater in space or whatever. And yeah, so the good news is that this is a very ambitious thing to say, okay, I'm going to identify the weak signals in this bandwidth, and I'm going to, just let me at it. So with the constraints of the power budget, and saying, okay, the ICE 40 is pretty much the go-to obvious choice, then you can probably do two or three. We would have to work really hard on making um, the HDL would have to be pretty with it. Like you would have to
Yeah.
work hard to get it to fit. But
I mean, part of the idea here as well for me is also that it doesn't all have to be an HDL. Like the
Yeah, right.
microcontroller there is pretty capable too, and it's always easier to write firmware than gateware, right? So part of the idea here was, can we sort of pick the key things that we really have to offload because the ARM core can't do them efficiently, and not try and do the entire project in gateware.
Right. There's a balance, as you well know,
Yeah.
between, it's a we call it like a three-legged stool, because you have general purpose processors that are constantly getting faster and faster so that you just brute force your problem. Then you have ASICs and FPGAs, and essentially hardware descriptive language path, with multiple different families of of chips, either an ASIC or an FPGA or whatever. And then you have GPUs, so graphical processing units are that third leg, generally pretty darn power hungry, generally not something that we would put on a 1 or 2 or 3 U spacecraft. So when we're figuring out how to solve a problem, we have these three different paths. And sometimes a path races ahead. Like you have a lot of advancements in general purpose processors over the years that have outstripped everything else. But what you offload to the hardware, to the HDL, to the FPGA, boy, that if you know what you're doing, which some of us sort of kind of have figured it out, but this is a very difficult sort of interdisciplinary challenge. So what you're talking about is load balancing to correctly choose what to give to the processor, what to give to the FPGA, and that is really like the core heart of software-defined radio. So it's super exciting, and I think that this is a fantastic project that is both innovative and interesting, but also accessible. And there are not very many of those, to be honest. I think all of us have experienced the owl drawing problem. And this is sort of a meme. It's kind of a joke. So when you're learning to draw an owl, the first stage is to draw 2 circles, one for the body and one for the head. And then the next step is it's completely done. And you're like, there's nothing in between. And a lot of times, firmware, HDL, FPGAs, embedded processing, it's like you get a hello world. And then, oh, here you go is a master's thesis, or some sort of PhD dissertation or something insanely hard. This actually hits a really good balance. So I'm very excited about this, and we'll do all that we can to try to help out and to provide practical designs. So it's kind of what we do is like as quickly as possible, we start, it works over the air, then it works. And that's what we could probably help with. I think we can probably help with some of the DSP or the signal design or comm theory stuff to kind of like where are the edges and what is it capable of. And I think we have a reasonable confidence on how on what it takes, to take this type of design. How many loops does it really take? How many lookup tables does it take? So a lot of us have done this sort of work for a while and have a good maybe sense. But there's always surprises, and amateur radio gives us an opportunity to do things that are unconstrained by the sort of commercial stuff, the craft that gets on there. So I think we actually can make some traction on sort of what you're talking about is sort of the observation or weak signal work side of this, and that could be a whole build. And with it being updated in orbit, we can actually have multiple configurations. You can have a time where it's totally focused and all of the resources are doing this weak signal work, and then other times it's doing what might be considered more pedestrian communications modes, the well-known stuff. So this platform is amazing, exciting, and I'd like to move forward and see what we can do to help make it real.
May I just
Yeah,
briefly
sure.
suggest something? Martin, hello. My name is Shodra N3RDX. I work in the space industry, but long before I joined the space industry, I designed a couple of spacecraft. And my interaction with Michelle over the years, I'll just summarize, has been kind of like I talk about things, and I want to do things. So I apologize for not showing up at the meetings interim, but I think I can help you. If you give me just about a minute or so, and I can share 2 slides. Is that okay? Michelle, could I share something so that everybody can see it?
Um, I think that's okay. We're actually technically over time, so I want to be sensitive to
Or,
people.
or, or I could just go offline and perhaps share with you and Martin if interested. It's relevant to the spacecraft bus design, which will
Oh,
really speed up your development path.
I think that could we maybe schedule something coming up here soon to actually focus on the bus design, because the design that Martin has introduced today is a development board. So
Yes, and I did see the board. I believe one side was 100 millimeters. I didn't see the other side, but generally, it's of a design that needs a little bit of adjustment to allow for the posts to be able to,
It's not intended as a CubeSat form factor design.
Oh,
This is a
okay.
development board. The idea, was to sort of see that you can see from the layout that with a bit of tighter packing, it can be packed
Okay.
into the 80 by 80 with the posts and the cutouts and everything. But it's
Okay.
not trying to meet that format at the moment. It's not really a prototype for flight hardware. It's a development board for the capability.
Okay, and
not
you,
yet, but
okay,
in
not yet.
the near future, we're going to start having to think about this because it's pretty clear that it's going to need to be a 1U card, that it's going to go into one of the 2Us available, that it fits in there in the bus. And so your background and experience, Shamundra, is going to be very, very critical.
I can also help with your
And
power issue. I can also help with your power issue. I'm thankfully one of the few people who really eked out power from 1.5 U CubeSat. You have power. I pretty much can blindfolded tell you you're gonna have a lot more power than you expect, but I need to
okay,
work.
good. Yeah, because we're, as you can
Thank you.
see, power limited is if we could like in order to do like the stuff that we might be more accustomed to doing, like some of the things that we've talked about over the past day or so, then 2, 3, 4 watts is really where that's kind of what you're talking about. So half a watt is kind of low for the more ambitious work. It's totally reasonable for some of the more I would say legacy or traditional modes in amateur radio. But more power gives us more capability. It's a direct one-to-one relationship. So yes, if it's okay with you, Shamundra, what we'll do is we'll schedule something coming up as soon as it looks kind of reasonable. We'll
Yeah,
start talking about that path and just keep
please,
talking about it. And
no, that's fine. I mean, I'm happy that ORI has hosted the knowledge base. I need to make sure that the knowledge base is understandable. Not many people read it and they couldn't understand it, so that's why they're. But I can help with the power and
okay,
the PCB design very fast. Okay, it's
cool,
done. Been there 10 years ago. Done.
right on. Okay, well, let's circle back on that and get it moved further down the road. Sounds awesome.
Thank you.
Yeah, thank you. No, we're over time. But I want to thank everybody for for coming, first of all, and spending your time. Once you spend it, you can't get it back, so it's priceless. The last person I'll check in with here is Rick. Rick, is there anything that you want to bring up or add or need to tell us or share or any of your thoughts about today? And then we'll close.
No, not much. I worked all most of the day yesterday on a new approach to collecting data for drift scans with the big dish. Ted and I have come up with a new data collection algorithm. Seems like it has promise, but we shall see. A lot of work.
Oh, that's exciting. If I'm assuming that you're going to do a write-up about it for this would be for DSES for the Deep Space Exploration Society. So I assume there's
Yeah.
going to be a like some sort of write-up or article about it. And if there is, then I would really like to put it in our newsletter. So let me know.
If I succeed, even in a small way, there'll be a write-up.
Awesome. Yeah, I'm really looking forward to it. Drift scan's super exciting and gets people involved. And then Adrian, I see that you're here, and hello, Adrian. So if there's anything that you have to
Hi.
share or anything that you want to chip in before we close, please do.
No developments. Had several questions regarding the AMSAT CubeSat, and I'm sorry I came in a little bit late, so I didn't quite catch the 160 meter antenna talk, but I'm sure I'll catch up at some other point. But the only question I had really on the weak signal, that was an interesting map about the overhead RFI that the previous satellite had captured, and so I'm sitting here wondering, well, on a future CubeSat comm, so is the person with a 100-watt ERP is going to overpower the 5-watt handheld that's going to try to do the uplink comm, and how is that going to be accommodated? But that's just from a very sort of unexpert sort of point of view from this. But anyway, no, excellent presentations, and that's about it.
To answer very briefly, that's kind of why I had this focus on the dynamic range of this and tapping this off before we go into the AGC that's part of the linear transponder path in this satellite design, and coming in with an ADC path with plenty of bit depth, so that if you've got someone at 100 watts and someone at 5 watts and they're, that many, I mean, you're what, 13 dB apart at that point, right? You've still got enough bit depth to be able to pick out those two signals, provided they're reasonably spaced in frequency and one's not splatting onto the other. That's viable.
Very good. All right, Adrian, anything else?
No, that was just a question that popped up.
Yeah, no, it's a good one.
I'm very anxiously looking forward to Rick's contribution. I come in from more or less his angle as a Sarah and also the SES member, so I'm really looking forward to what he can contribute for the drift scan for hydrogen line or anything else. Actually, interested in masers too. Is that applicable for hydroxyl masers, for example? But anyway, yeah, looking forward to see what he can come up.
Yeah, very good. Okay, and so our newsletter will come out. Open Research Institute has a newsletter. It's called the Inner Circle, and we have a double issue. So this will cover the past 2 months. That's going to come out maybe today, maybe tomorrow. We'll send out a PDF to the mailing list, and we'll post all of the content on our website, both as individual articles and as a sort of a one-stop article. And then it'll also go out as a HTML email newsletter to all of the subscribers on our list. So that is what will happen shortly. That's been a joy to help do. There's a variety of articles in there from a number of folks. And if you are interested in writing for our newsletter and sharing your work, then please do. And that's happening. We've submitted several articles to both QST and QEX. That's the ARRL, American Radio Relay League. That's our big national amateur radio organization here. One of them was about the day that we spent at Doinalo, and it was a real joy. It was a real privilege to be able to do that. Looking forward to Earth, Venus, Earth work coming up in October of 2026. And plenty else going on. Thank you, everybody, for sharing your time with us today. We'll do it again next week. And please join us on Slack if you can. That's where the daily engineering and discussions and all the sausage is made there. We do have an email sort of announcement list. It's fairly low traffic, but lets people know what's going on. And then everything that we do is published in our GitHub. And let's see, I don't know of any next big conferences or presentations coming up. There might be a few that are online. Some of our friends are doing some artificial intelligence presentations, have a lot of amateur radio crossover. So looking forward to that and coming up in November. Okay, everybody. I'll pause for any last quick announcements before we close. And yeah, thank you again for coming. All right. See y'all soon.
Right. Thank you. Bye.